Okay, so we're going to start a new topic right now called linear independence. You have a question in the back.
Yes.
Yes.
Have you made it available for us to actually see your lecture slides yet?
I did on Friday using a certain website. Whoops. But then the power went out, and my computer in my office where I happen to be running this website didn't turn back on when the power came back. So it was a problem. But this is, I turned it back on this morning.
Okay, I just checked it.
Yeah, https://cloud.sagemath.org. At this very second?
Yeah.
Okay. Well, did you put an S there?
Oh.
Because the S is very important. I haven't set up an automatic redirect to the secure version of the site, because that just takes, I have to modify Apache on some server to do that. Yeah. So I actually bought 4 machines that are in the UW tower in the room with the generator, like the enterprise server room, but I haven't deployed this on there yet, though that will happen in a week or two. And that room did not go down during the power outage, which is pretty cool. It's the only thing on campus, I think, that didn't go down. Unfortunately, it didn't matter because I didn't have the site deployed there. It kept up some other sites though, that I have. Okay, so let's start with linear independence. And I want to recommend that you read section 3.5 of the book before Wednesday, or class on Wednesday. It begins with the sentence, "This is the most important section of the book." So if you read only one section ever, this is the one to read. It's about, well, you'll see. I'll start talking about this sort of stuff. So we're going to introduce some ideas that will help us understand much more precisely what's going on when you have a system of linear equations and there are several free variables and some non-free variables, and you get some answer, but it's kind of maybe tricky to understand it geometrically. We're going to get a much better idea of what's going on geometrically behind the scenes. And we're going to introduce kind of a whole new idea that goes beyond just systems of equations and matrices. And that's the idea of a vector space, which I will not define today, but we will talk about this carefully this week, but just not today. So what we're going to do today is just introduce a seemingly simple seemingly innocent sounding definition, which is linear independence of vectors. And then we'll do a whole bunch of examples to make sure you can understand the definition and work with it. And that definition is going to be absolutely crucial in understanding this idea of vector space later and using it later this week. Okay? So this is what we're going to go for, is linear independence. First, I'm just going to write down a definition. And it's down here. Actually, I want to just clarify something before I do that. But I'm going to write down a definition of what it means for a set of vectors to be linearly independent. And then I'm just going to ask a whole bunch of questions to you, some of which will seem very, very easy at the beginning. That are just a matter of getting familiar with that definition. Okay? Before we do that, though, I've mainly talked about matrices and not vectors in this class. And for the purposes of this class, I'm going to use the word vector to simply mean a matrix with one column and n rows. So an n by 1 matrix. That's nice because then matrices are simply a special case of, or sorry, vectors are then just a special case of matrices. So a vector is an n by 1 matrix. Here's an example, 1, 2, 3, 4. So this is a 4 by 1 matrix. It has 4 rows and 1 column. So when I say vector, typically I will mean simply a matrix with 1 column. However, especially in the notes, it's very hard to write a column because it takes up too much space vertically and you can't put it inside of text. So I will sometimes also write a vector like this, 1, 2, 3, 4 in parentheses, just because I don't want to have to write it vertically. especially in the notes. On the board, I'll almost always write them vertically. You may have seen vectors in other classes often, and you think of them often as an arrow that goes from the origin to some point in space. You've seen vectors thought of that way. And there's a correspondence between that and this. You just take this point, and you go from the origin to that point, and that's the arrow that you're thinking of. Where the point right here would be the point 1, 2, 3, 4. Also, the collection of vectors, so all vectors with n entries that are real numbers. Oops. So that's a set we're going to consider a lot. And I'll just denote it by Rn. And because I'll use that a lot, I'm just going to recopy exactly what I just wrote over here. So Rn equals vectors, all vectors with n entries, n real number entries. So it's just a set. So for example, R1, you can think of it geometrically as an infinite line. R2 is the plane. R3 is three-dimensional Euclidean space. R4 is 4 tuples of real numbers. R5 is all 5 tuples of real numbers. R6 is all 6 tuples of real numbers. Okay? And sometimes instead of R, it'll be good to consider C, the complex numbers. Exactly the same, except instead of n tuples of real numbers, you take n tuples of complex numbers. So this is all n tuples of complex numbers. And another one that's often useful is q to the n. This is all n tuples of rational numbers. A rational number is just any fraction. All n tuples, or by n tuple I mean vector with n entries of rational numbers. Or rational, that just means a fraction. Oops. And in coding theory, for example, when people make CDs, they try to make it so that if you scratch your CD, it doesn't mess up the music. They use another object very similar to this called GFP. This means Galois field. It's a so-called finite field. So it's just another example of this sort of thing. You take n tuples of numbers between 0 and p minus 1, where p is a prime. Often p is 2 in the case of CDs. So a Galois field. So it's just, GFP is just numbers from 0 through p minus 1, p of prime. So this is used for CD error correction. I don't think that this is used for MP3 files, but it's used for CDs. Okay, so those are just different examples. This is the one we'll work with by far the most in this class, n tuples of reals. But when we do examples, almost invariably we'll always work with q to the n, because rational numbers are easier to write down. I mean, it's kind of silly to do examples where you have numbers like pi and e and so on as entries in your matrix, because you just end up with, they don't simplify very nicely. Okay, any questions? This shouldn't be hard, it's just some notation. So if I say, consider R3, you can think three-dimensional space, where you just take all triples or all matrices with 3 columns and 3 rows in 1 column. So this would be an element of R3. Actually, let's do a little practice. I'm going to write down a couple of vectors, and you should tell me which of these, and your answer will be something like R7 or C2 or Q5. Okay, that's the sort of answer. So let's do it. Okay, I'll write down a vector. As a column vector. Okay, which of those is it in? Q2, excellent. Okay, I'll write down another one. Which is that in? Excellent. What's that in? Okay. Q, nope, not Q because that pi. It's certainly in C4, but it's also in R4. Because in fact, R4 is contained in C4. And yeah, some containments here. Q to the n is contained in R to the n. It's contained in C to the n. So try to choose the one that's the smallest that contains it. Let's see. 1, 2, let's see. How about the sum of 1 over n squared? N goes from 1 to infinity. Which one is that in?
Q3.
Nope. I think Euler proved it's not in Q3. R3, yes. It turns out the sum as n goes from 1 to infinity of 1 over n squared converges to pi squared over 6. Pi is not a rational number, and so this is in R3. Okay, so that's great. Seems like you, yes?
Would it be possible for a vector with 2 rows to exist in R3, even though it doesn't have all
No, it would be in R2, because it has 2 rows. If you, yeah, you should just think of it as being in R2. It's often, it may make sense to put R2 inside of R3 somehow, but there's lots of different ways you can do it. Like you can make it the XY axis, or the XY plane, or the YZ plane, depending on what you're doing. So you may specify, or a problem might specify, we embed R2 inside of R3 as the XY plane. And then a vector with 2 entries would then be identified with those 2 entries and a 0 at the bottom. But you'd want to make that explicit, I think. Yes?
What does the E symbol type?
Where did I put the E? Oh! The element symbol? Ah, right here. Sorry. This means is an element of. It's an epsilon, a Greek letter. So somebody might write pi. So if I were to say to you, pi is an element of the real numbers, would that make sense to you or not? Pi is an element of just means is in the set. So this symbol right here means in the set. So it means the thing on the left is in the set on the right. So in short, it means in. It's just a symbol for in.
And the other one means contains it.
Yes. Yeah, this means is a subset, or is contained in. Is contained in. So for example, you could write with this, the first vector is in Q2, the second one is in C2, the third one is in R4, and that one's in R3. Yes?
So I'm just a little confused why the top left one's in Q2, but the bottom left one's in R4.
Okay.
Because the 1.2 wouldn't that be
So,
considered?
yep. The 1 is a rational number, which is fine. The 5 is a rational number. The 1.2 is also a rational number. But unfortunately, that number pi right there, 3.1415926.5, etc., that is not a rational number. Yeah. It's not obvious that it's not a rational number, but it's a fact that it's not a rational number. It can often be very difficult to decide whether or not something's a real number or a rational number. Okay. Yes?
All of the rational numbers are real numbers, right?
That's correct. Yes.
Yeah, so is it safe to use real numbers as reason?
Yes, absolutely. And in fact, that's why you'll see that frequently throughout the book and in the problems, your vector will just be in here, which is perfectly fine because the rationals are contained in there. Okay, any more questions?
Is it the same principle if it's 1 by n matrix?
You can also, yeah, yes. Yeah. Yes. All right, so that's what vectors are. And now, let's talk about one single definition that involves vectors. And we're not going to get the span. All right, so here's the definition, which I will now slide up here. Oops. Go away, I'll use stuff. Okay. Here it is. Definition. Very important definition. So if you have some vectors, a little set of vectors, v1 through vk. So this means a collection of vectors, and we're going to assume that they're all, I'll even use this set notation. So I'll just say v1 through vk, and they're all in, let's just say Rn. You'll be able to make the same definition if they're all in C to the n or whatever. Doesn't really matter. So if you have such vectors, we say they are linearly independent if whenever C1 V1 plus dot 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 plus CK VK equals 0 for C1 up through CK all real numbers, then C1 equals C2 equals dot 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 equals C sub k equals 0. This should feel a bit uncomfortable to you and take some time to absorb. So if you're like, huh, if that's your first reaction, that's very natural. That should be your first reaction. Okay? So the first thing we'll do is I'm going to write some examples of a collection of vectors, and we're going to try to decide whether or not they're linearly independent, whether or not this phrase linearly independent applies to a collection of vectors that I'll give you. And we'll just do this for a couple, and hopefully as you see this, what this means will start to click. And I'll also point out some ways in which it's related to things you've already seen. It's really just kind of an abstract way of restating that a certain system of linear equations only has the zero solution. That's really all it's saying. Actually, I'll put that in a box right here, just right now. Equivalently, let me explain why this is. Equivalently, if you take the matrix whose columns are v1 through vk, and you imagine multiplying that matrix by x and getting 0, then this equation in x has only the solution x equal to 0. So that's the only solution. Because what does this definition really say? It's kind of a contorted way of saying that if you take any combination of the columns, so here, if the entries in this vector x are c1 through ck, when you multiply the matrix whose columns are v1 through vk by the vector whose entries are c1 through ck, then you get exactly c1 v1 plus dot 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 plus ck vk. And this complicated looking definition just says that no matter how you do this product, if you get 0, that is, if you have a solution to this linear system, then your solution is 0. So there's a unique solution and it's 0. That's what it means for a collection of vectors to be linearly independent. That's a different way of restating the definition, an equivalent way. So now let's practice with this definition to get a sense of what it really says. I'm going to write down some vectors, and then we're going to decide whether or not they are linearly independent. Okay? I'll start with some ridiculously special cases. That's okay. So I'll just call these example 1. So I just have to make up some vectors. I'll say v1 is, make this as easy as I can, the vector 1. Okay, so there's exactly one vector. It's sitting in R1. Is this set of vectors linearly independent? What do you think? Yes, because if you had c times v equal to 0, that would be c times this equal to 0. That would force the c to be 0. So this is linearly independent. So this set consisting of v1 is linearly independent. Yes. All right, let's do another one. Let's say v1 is number 1, and v2 is the number 5, or the matrix with the entry 5. Is this set of two vectors linearly independent or not? I hear a no. I hear more no's. I hear a lot of no's. Is anybody really confident in your no? In your knowledge? Well, everyone who said no is right. This is not. These two vectors are not linearly independent. Circle them in red. They're not linearly independent. And here's why. First, I'll just formally using the definition. Linearly independent says that if there's any way to write c1 v1 plus dot plus ck vk equal to 0, then the numbers that you used had to be 0. But I'll give you a way of writing those two vectors, something times 1 plus something times the other equal to 0, and the coefficients won't be 0. Okay? Watch this. Minus 5 times v1 plus v2. What's that equal to? 0. Because minus 5 times that is minus 5, plus 5 you get 0. Are the coefficients, which are minus 5, that's what c1 is, and c2 is 1, are those coefficients both 0? Rhetorical question, they're obviously not, so these vectors are linearly dependent. Okay, suppose I write down 3 vectors in R1. I don't even tell you what they are. Is there any hope that they're linearly independent? Okay, why? Why do you think there's hope that they are linearly independent? Right, that will make them linearly dependent. Yeah, that's what you're thinking. Nope, but it's okay. You answered, well, you answered very clearly my badly worded question. Yes, thanks. Yes. Yeah. Good question. He asks, if they were all the same, would they be linearly independent? Nope. Because then you could easily do minus 1 for that coefficient, plus 1 for that coefficient, and 0 for that one. So that doesn't work. I think you're pretty convinced there's no possible way that you can make them linearly independent. They're always going to be dependent. Yes?
Well, it's like in the first matrix, in like the 1, 1 entry, you had something, and the rest of them were all 0.
Okay, that's a great question. He asks, if this is some number, let's say not 0, and these are both 0, is this collection of 3 vectors linearly independent? According to this definition. What do you think? Why? Why not? Yeah. You can just put anything you want here. Like you can do 1 times the first one, actually 0 times the first one, you better do that. And then anything you want at all, say 1728 times the second one, and you'll get 0. And that's not 0. So no matter what you do with the A, these are linearly dependent. linearly dependent just means that you're not linearly independent. So you could say that. Linearly dependent equals not linearly independent. Okay, great. So you're pretty good at the case when n equals 1. Let's try some examples when n equals 2. All right, so first example, I'll make v1 be the vector 1, 2. Okay, is this the set consisting of this one vector? Is it linearly independent? Yes. Because, just using the definition, there's no way that you're going to have, if you have something times that vector equal to 0, the coefficient out front has to be 0. Okay, so this is linearly independent. All right, let's do another one. If I take v1 equal to 1, 2, and v2 equal to 2, 4, is the set consisting of those two vectors linearly independent? A lot of people say no. Why? Exactly. Notice, you're perfectly right, minus 2 times v1 plus v2 equals 0. These coefficients aren't 0. So whenever you do that, when you give a relation that looks like this between your vectors that's equal to 0, that's called a linear dependence. Like you've given a way in which the vectors depend on each other. v2 depends on v1. It's just a scalar multiple of v1. So that's what this thing is called. It's a linear dependence. And vectors are linearly independent if you can't give any linear dependencies thrown into them. All right, let's do another one. What about v1 equals 1, 2, and v2 equals 3, 4? Are these linearly independent or not? What do you think? Linearly independent. Yep, they are linearly independent. Because there's no way. How do we show it? We have to actually show something now that there's no way. You have to think a little bit more that there's no way this could happen. Well, let's just think about it. If you had c times v1, c1 times v1 plus c2 times v2 equal to 0, what would happen? So if c1 were 0, then you'd have c2 times v2 equal to 0, and that would tell you that c2 has to be 0, because v2 is 3, 4. It's not 0. So c1 is definitely not 0 if you have this and they're not 0. So if c1 or c2 is not 0, then you have this with c1 not equal to 0. Then you can just rescale, and you end up seeing that v1 is minus c2 times v2. So v1 is a scalar multiple of v2. But it just isn't. I mean, look, at v1 is not a scalar multiple of v2. So you get a contradiction. Yes?
So, depending on the number of rows of the vector,
Yes.
does that mean that if it's not a scalar multiple, then you're going to have, say, there are 3-row vector, that you can have 3 different things that are all linear independent? Is it proportional to the number of rows?
If there's 2 vectors and under consideration of k equals 2, your intuition about how things work is exactly right. Linearly independent, if you have at most 2 vectors, well, if you have exactly 2 vectors, just means that one is not a scalar multiple of the other. Unfortunately, when you get to 3 vectors, it gets much more complicated. Yes? Or a little bit more complicated.
Problem thing that is, because you can rewrite matrices so many ways,
Mm-hmm.
do you have to go through a lot of sort of grunt work to figure out if they are scalar multiples of each other? Because I mean, if you can just add rows to wherever.
Yeah, it gets complicated. That's exactly the problem.
Okay.
Yep. It can be very difficult to tell whether or not a collection of vectors is linearly independent. If there's only one vector, you just ask yourself, is the vector 0 or not? If it's the 0 vector, then that one vector is not linearly independent. But if it's not 0, then it is. If there are two vectors, you ask, is one a scalar multiple of the other? If so, then your vectors are not linearly independent. So notice in the pictures here we have 1, 2, and then 3, 4 is more like that. So, and this works for any n at all. If your vectors are not, if you don't have one being a scalar multiple of the other, then they're linearly independent for two vectors. And then it just gets more complicated for three vectors. But it's kind of similar geometrically. I'll show you that with 3. I don't really want to erase the definition. But I might have to. Here, I'll put something here. All right, so let's just look at the, just enough time to look at these two examples. Actually, let's just skip to the last one. So here's three vectors. V1 is 1, 2, 3. V2 is 4, 5, 6. First, are these linearly independent? If you take those two vectors, do you get something that's linearly independent? Is that a linearly independent set of two vectors? Yes. Notice that the second one is not a scalar multiple of the first, and using similar reasoning, you can just see from the definition, these are not linearly independent. I just said that wrong. These are linearly independent. These are linearly independent. So I'll circle them in green to suggest their independence. Now what if I throw in a third vector? V3 equals 7, 8, 9. Are these three vectors linearly independent? It's certainly not the case that any one is a scalar multiple of the other. When you come back on Wednesday, know whether or not these are linearly independent. Figure it out somehow. Possibly by using this equivalent formulation.
So did you get those emails I sent you? Or
Where did you send them?
to the 2015 UW 308?
I might have. I probably did.
Okay.
I just didn't answer.
So I'm just wondering if